Well, imagine that we have water or some kind of liquid flowing through a pipe with a fixed diameter. Then the fluid flows with greater velocity near the center and with less velocity near the edge, because at the center there's no friction like there would be at the edge. Anyway, the following example could be a model for such a situation. All right, so think about this one hard.
Focus.
Yes, we must focus. So we're going to sketch some of the vectors. In the velocity field, v of xyz is 25 minus x squared minus y squared times k. So there's no I component, no j component. These vectors are all pointing north, so to speak. They're all pointing upward. Where x squared plus y squared is less than or equal to 25, that means our pipe has a 5-unit radius, a 10-unit diameter, and is a circular cylinder along the z-axis. So here's our pipe, and I just kind of illustrated the vector field of the points in the xy plane, wherever that may be. But the mesh just shows the tips of the vectors from the xy plane, but you understand up here there's in this plane, maybe where z equals 20 or something like that, there's a set of vectors that looks just like this. So this is a vector field. All these vectors in the middle are longer than the ones towards the edges because of the friction from the edges of the pipe, and the water in the middle is faster. Think about a river where there's a swift current. The water is always fastest in the middle, unless there's obstructions of sorts. But same kind of idea. So looks like the vectors are normal to the level curves from which they emanate, and that's a property of gradients, if you recall. So some vector fields are really just fields of gradients for a differentiable scalar function f, and these vector fields that are fields of gradients for a differentiable scalar function are called conservative.